What today is? It's Thursday. So that falls for.
You guys watching the videos that I posted like last week? Because
No,
I'm not
I wouldn't be
gonna
excited for
do it again and just watch the video. Not all the content in the video will be asked for in the exam. I'm gonna tell you where I'm gonna stop in this chapter because there's a part that is really hard to digest. I'm not gonna give it to you in this class. It's about the slip motion, like when you have two like motion with a slip. So we're not gonna include this. We're gonna include the regular motion. So I'm gonna tell you what minute exactly in the video that you should stop at, and this is gonna be included in the exam. So there's a big chunk in these videos that are not gonna be included. Today I'm gonna start with chapter 17. So okay, so when you have the acceleration, there should be a part that says this is the slip part. So this is not going to be included. We're going to stop at the motion that without the slip. So we're not going to include this. Today we are going to start with chapter 17, which talked about the Newtonian kinetics for rigid body. Right now, what was that?
Do you just have the lectures?
No, I didn't got time, but I'm gonna post it after the class. Yeah.
Thank you.
Alright, so over the last couple weeks, we have been studying how we can identify the velocity, the displacement, the acceleration of the rigid bodies. The same thing that we did with particles, we need to know what is the Newtonian kinetics. If there's a forces acting on a rigid body, what is the acceleration of this body? What is the work on this body, which is the next chapter. We will see how far we can go. But today we are going to start the Newtonian kinetics. But before we start this, we cannot start it without the background on the moment of inertia, or the mass moment of inertia. But let me write here the chapter name. Chapter 17. Kinetics of rigid bodies. Alright, so when we say Newtonian, what is the first thing that comes to your mind? Which is the sum of the forces is equal to the mass multiplied by acceleration, right? Okay. So the mass multiplied by acceleration. This is the first thing that came to your mind, okay? When we say Newtonian, so this is the first thing that you have to write it, okay? So, but this was enough for particles. Like if you have a particle, so you only care about, well, how's the translation of this particle look like? But when you have a rigid body, this rigid body can make a rotation about its original axis, like can make a rotation about this axis, can make rotation about the center of mass. So that's why we need to include moment. When we have a particle, like if we consider this as a particle, okay, so we don't care about this particle is moving around itself or not. So because it's like all the mass is larger than one small area, and we are considering that this mass is very small. That's what we consider particle. Or it's a big and it has a uniform translation, doesn't have any rotation. But once we talk about rigid bodies that is very big and can rotate, so we need to add the moment. The sum of the moment of the body is equal to, so we are gonna replace the mass with something that's called the mass moment of inertia, I, multiplied by the angular moment, which is alpha. Okay, so this is the second equation. As an engineer, or specifically as a structural engineer, all our life is about forces and moments. That's all what is our life about. If you're a structural engineer and you have, for example, a bridge, a beam, a slab, anything that is supported like this, I need to know what is the reactions, which is forces. I need to know what is the bending moment on our slab. So our life is all about some forces and some moments that we all talk about in any engineering problems, okay? In any structural engineering problems, okay? So now we have forces, we have moments. This is the equation, the second equation, like the mass multiplied by the acceleration. Here is a similar one, but it's the mass moment of inertia. So let me write here, mass moment of inertia. And here this is alpha, which is the angular acceleration.
What's the difference between mass moment of inertia and area moment of inertia?
Okay, so that's a good question. All right, what is the mass moment of inertia? The mass moment of inertia is the resistance of the mass for rotation. And that's what we use in dynamics. This property, if you have, for example, this mass, we need to find what is the resistance of this mass to rotate. Okay, so that's what we call the mass moment of inertia. The area moment of inertia is something that we can describe what is the resistance of the cross section to bending moment. Like, okay, like for example, if we have a beam, like the one over there, and I take a cross section here, and this cross section is something like this, right? So if I want to find what is the resistance of this cross section to bending moment, I need to get the area moment of inertia, okay? And that's actually what we use in structural engineering. We don't use mass moment of inertia. We always use area moment of inertia. And let me ask you, if the area of the cross section got bigger, what will happen to the area moment of inertia? It's gonna get bigger, right? Like if I have this floor supported by a beam, and I found that this beam is gonna fail with the original loads that it has, so I need to increase the cross-section area. But let me tell you something. This cross-section area, I know that you guys have some background in moment of inertias, right? You take it either math, statics, right? So here, this section has a moment of inertia, or what we call moment of inertia, area moment of inertia in this context, about this axis different from this axis. So let me ask you, I have this cross section when I cut here, and this beam has loads something like this, okay? So what I care about is the moment of inertia about x-axis or the moment of inertia about y-axis. X, y, I mean like y is x, because if the load is coming here, this cross section is gonna bend this way about x-axis, so that's what I wanna increase. Like for example, if you are designing this beam to carry this load and you find that this section is not enough to take this load and you need to increase the stiffness, increase the moment of inertia, I need to increase the depths because I need to more inertia about x-axis. Why? Because all the loads is coming this way. But let's say if the loads is coming this way from the other side, not this way, like this beam is not gonna bend this way, it's gonna bend this way. So it's about y-axis. So I need to increase the inertia about y-axis. So I need to figure out where the loads are coming from, how is the cross section is gonna bend, and this is where I want to increase the inertia. All our loads are vertical, so we always care about the depth. Unless, for example, if you have, sometimes there's some hangers that has like a crane, and this crane is hitting a beam from a, so it makes the bending sound. So you need to study the loads first before you decide where inertia to consider. But usually, we always care about the depths. However, there's some standards that needs to have like a ratio between depths and widths. Like you cannot have a very, very deep section and very, very thin. So there should be aspect ratio between the depths and the widths. You need to maintain this ratio. So that's usually when you go to hangers, when you see the beams, it's always deep and thin. So it's always going down, not going this way. Why? Because all the loads are going down, so you need all the inertia is about x-axis. So this is when we start talking structural engineering, so we care about the area moment of inertia. But right now we are doing dynamics. We want to study if this mass is gonna rotate or not, like about a specific axis. So we talk about mass moment of inertia. And I believe I only use mass moment of inertia at the dynamics classes. Moving forward, we only use area moment of inertia in all the structural engineering classes. Specifically in mechanics of materials. I'm not sure if you guys started with mechanics of materials. You should deeply get into this and and you should like be able to get like the moment of inertia about xy, about y, so you should have a pretty good background on this. Okay, so let's get back to the mass moment of inertia. All right, so there's some, you guys tell me, because since you guys take some classes, if I want to get the mass moment of inertia, it's right here, mass moment of inertia. And I'm gonna say it's I. If I want to get, for example, if I have a body like this, and I want to get the mass moment of inertia about this axis, how can I get it? So to get the moment of inertia about any axis, like let's say this axis, and you have a mass here. First, you need to get the mass moment of inertia about the CG of the mass, and then transfer this mass to be here. Okay? So that's what we call the barrel axis theorem. Okay? So this is the first thing. But let's say that we have our body here, like zoom in on this body, and become this body, and this is where the CG at, like let's assume it's here. And I want to get the mass moment of inertia of this body about the CG. So you need to get the moment of inertia of each small particle of the mass about this axis. Like if there's a mass here, this is a small particle, I need to get the moment of inertia of this small mass about this axis, and every single piece of the mass. So since you have a small part, and you want to get all the moment of inertia, of all the mass in this body, so we need to do integration. So to do this, is the function is, it says that you need to integrate r squared dm. What is that? Like if this is your small mass and it's at a distance r squared from the axis that you want to get the moment of inertia about, so you need to do an integration for the multiplication of the r squared multiplied by your mass, and then you integrate to get all the moment of inertia of all the masses around this body. Okay? So that's why we took an infinitesimal mass and then multiplied by r squared, so that's actually the moment of inertia of this small mass, and we call this di is equal to r squared dm. But if we want to get I of the entire body, so we need to integrate over the whole body. Alright? Okay, so and do you guys know the relationship between the mass and volume? The mass equal how to get the volume, or the mass equal like as a function of volume. You know that it's rho multiplied by volume. It's the density multiplied by the volume of the body. You guys know that? Or you guys know that rho, the density, is the mass over the volume? Okay, so density, the density of the body is equal to the mass over the volume. So if I want to get m, so it's going to be rho v. If you want to get dm, it's going to be, rho is constant. Any depends on the material. So if you have like a metal, it has a rho. If you have the air, it has a rho. Every metal, it has a rho. So rho is always constant, and this is dv. So actually we can replace this by the integration of r squared multiplied by rho dv. And we can get the rho out here, and we only leave the r squared multiplied by dv. So you have r and you have v, and definitely dv is function in the r somehow. So you need to find out what is the value of dv as a function in r, and then do the integration over the entire r, like let's say from r equal to 0 to r equal to capital R. That's actually how to do, or how to get the mass moment of inertia. All right, and I'm not sure if you guys know the barrel axis theorem. Right now, we have this is the CG, and we get the mass moment of inertia about the CG. But let's say, what if we want to get the mass moment of inertia about different axes at a distance? For example, let's name it like here, d, from the CG axis. Okay, so it says that the I about any axis, I about any axis is equal to the I bar. I bar is the moment of inertia of the body about the CG, okay? Plus the mass of the entire body multiplied by the distance d squared, this distance. That's what's called the barrel axis theorem, and actually I proved it here in my notes, so if you want to look at the proof, you can double check it. So here we have the barrel axis theorem. And what about composite bodies? Composite. Sometimes, for example, we can have a body, something like this. So it's a composite body, like you have a rectangle and a rectangle, and maybe it has a circle that is out. So a body something like this, and it has a hole. So that's what we call composite bodies. To get the mass moment of inertia about this body, we need to divide it into a triangle, and a rectangle, and minus a circle. So to get the mass moment of inertia, and we say that, for example, if you want the mass moment of inertia about this axis, like let's say xy, so if you want to get iy, so you have to get the summation of the I bars plus md squared. But this is plus md squared, and all like always the mass moment of inertia is positive. Like I'm saying here, all mass moment of inertia of positive masses are positive. But you will tell me, is there a negative mass? Yeah. Mathematically, yes. Physically, no. Mathematically here, I have a void. To solve this, I need to make a triangle, positive mass, and make a negative mass, which is the surface. To solve this mathematically.
So you could also take like a big square and then subtract two
You
triangles.
definitely can do it in many different ways. But it's gonna be the same thing, but you can subtract this, and maybe you can end up having another thing here. So you'll have to figure out a way. There's different ways.
Yeah, but
Yeah, you definitely better take the easiest one. Okay, I have 1, 2, 3, and 4, and this 4 is minus. Right, so this is how it looks like, and I put the rules for the composite bodies. All the masses, all the positive masses has positive moment of inertia. Moment of inertia through the centroid is the smallest possible. Like for example, if you have a mass like this, and you get the mass moment of inertia about the centroid, is it going to be bigger or smaller if you got the mass moment of inertia about this axis? This is x1 and this is x2. Which one is bigger? If I get the mass moment of inertia of this body about its centroid or about this axis? Number 2.
number two, yeah.
Number 2 is going to be bigger. Why? Because it's going to have md squared into it. Okay? So it's going to have the mass moment of inertia about the CG, and then plus the term of md squared, the mass multiplied by this. Okay? Alright. There's one other thing that I want to talk about. I'm not sure if you guys heard about it. Something is called the radius of gyration. Have you guys heard about the radius of gyration?
Yeah.
Do you guys understand what is it? Really? No, don't look at my new notes. You guys tell me, what is the radius of gyration? I'm gonna tell you. The radius of gyration, it just has a good principle. Like, okay, let me tell you what we do in a steel design. In a steel design, when you design, for example, a roof or something, there's a bunch of I-beams. But each I-beam has different dimensions, different flange dimension, different web dimension. So sometimes, like you can see an I-beam and see this is small and this is bigger, but this is bigger because it's taller, but this one is more wider. So you cannot judge it from the dimension. You need only one number to tell you if this is more stiff than this one. And that's what we call the radius of gyration. We look in the tables for the radius of gyration of this, and you will find that this is much stiffer than this one. But let's just see what is the radius of gyration. We just said that if you want to get I is equal to of any mass is equal to the integration of the r squared dm. Okay? That's how we get the I. we will make, like, let's say we have a funny body, like, let's say a funny body is something like this. And the CG of this body, and let's say we want to get the mass moment of inertia about this axis. This is my XY axis. Alright? Okay, so if I want to get the mass moment of inertia about this body, so I need to integrate dn multiplied by dr from this axis. Or I get the mass moment of inertia about the CG and then transfer the CG to the y axis. Both of them is going to give you the same thing. If you want to get the mass moment of inertia about this body about y, you can get every mass and multiply by the r distance. So this is dn and this is dr, but it's going to be very, very different. So that's why we get about the CG, for example, here, and then once we get the mass moment of inertia by the CG, we multiply all the mass as a one single mass by the squared so that we can transfer about y. Let's say that we get this value. We make this value equal to something that's called k squared multiplied by all the mass without doing any integration. And what this means? This means like if you melt the whole mass and we make it like a single thin bar, something like this. Like let's say that we melted this mass and we make this mass as a one single bar, something like this. This bar as a mass is equivalent to this one, but is at a distance k from the axis that we are taking the moment about. So, and what this means to me, that means like I can get this, all the masses, like if you have another funny shape, something like this, or something like this, I can compare all of them. I melt them in one single bar and see how far they are from a fixed axis. The more that they are farther, which is the more is the radius of gyration, that means that more they have more mass moment of inertia. So it's like find a common ground for all the masses to compare between them. Do you guys know what I mean? Like you have, like I have a mass like this, and I have a mass like this, and I want to compare between them. So what we do is, let's say that this mass is relative to this one, okay? And I convert it to this bar. And this mass, I convert it to this bar, okay? So you convert it to one single mass, and then you find where they at, and K is measuring if they are more stiff or more mass moment of inertia or less. So if think about it, it's like a common ground to compare between different bodies. The more is the radius of gyration, the more is the mass moment of inertia. It's kind of like an index. Think about like an index to see how's the mass moment of inertia look like. So basically, you have to get the inertia, and then you have the mass if you want to get K. So K is going to be equal to root I over n. That's what is the radius of gyration is. Okay. There's another quantity, I'm not sure if you guys heard about it. It's called the radius, the center of percussion. We're not going to use it in this class, but we have to know it. It's called the center of percussion. You guys know what is the center of percussion is? Okay, so the center of percussion is the point at which an impact produces no reactive shock at the point. And the application of the center of percussion is like if any of you is playing baseball, playing tennis. So there is a point on the bat of the tennis bat or the baseball bat. So at this point, if the ball hit that bat, you will not feel any reaction in your hand. So if the ball hit in the far tip, you are gonna feel some reaction in your hand. But that's actually a trick that the professional players know. If he hit this ball at his bat, you are not gonna feel any reaction in your hand. That's what we call the center of percussion. So let's say, and the same thing actually with the hammers as well. Anything that hits something. There is a point on the hammer or the point on the pad that if it's hit something, you're not gonna feel any reaction. Like let's say that we have a hammer, something like this. The hammer has something here and a piece of metal. percussion, we call it Q node, is equal to the mass moment of inertia about the point, like let's say if this is the point that you are looking at, so about this point, equal to IO over the mass multiplied by Y bar. Let me tell you what these quantities is. Okay, so the first thing that you need to find the centroid of the whole body, not only one of them. Actually, the centroid of this is here, and the centroid of this is here. So the first thing is you need to find the centroids of the composite body. So what do you guys think? Where can be the centroid of this composite body? Is it gonna be here, 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 here? It's gonna be something in between these two masses. Definitely it's not gonna be here, and definitely it's not gonna be here. Something in between. And let me ask you something. Is it gonna be closer to this or this, and depends on what? If this has much more mass, like if this is metal and this is wood, so this is gonna be much more closer to here, and that's actually what is the hammer is. There's a piece of wood and there's a piece of metal, so the center of mass can be something here. So it's gonna be shifted a little bit. And the less this mass is, the more this center is gonna go towards, if this mass is 0, so it's gonna be coincide with this point. Okay, so here, let's assume that here is the center of mass of the entire body. Let's call it G. Alright, and the distance from the center of mass to the point O, this is what we call Y bar. Y bar, that means the center, where is the center of mass with respect to the origin. And the center of percussion can be something in between here, like can be, for example, can be here, like this point. This is the center of percussion. If I want to find it, I need to get IO, which is the mass moment of inertia of this and this about point O, and the M, the total mass of the whole body, this and this, you have to sum them, multiplied by Y bar, and then you can get QO. So it's a simple rule. You calculate the mass moment of inertia, you have the mass, you have the centroid with respect to point O, you can get the center of percussion. We are going to have an example that clarify how we can calculate.
The inertia is with respect to point O, right?
Yeah.
So you have to do parallel axis.
You can pick this point, you can pick this point, whatever point, but this, all of them, like
Have to be consistent.
Y bar is measured from the point that you are taking the mass moment of inertia at, and this is going to be measured from the same point. You can take a point here or a point here, whatever the point that you would like to pick. Okay, so let's solve an examples and see how the reality looks like. Example. Right, we have a cylinder. By the way, all the mass moment of inertia rules, you are gonna find them here. Okay, so you'll find the mass moment of inertia. Okay, let me talk about this first. Everybody can have a mass moment of inertia about any axis, but when we talk about bodies like this body, the main axis is X, Y, and Z. I can ask you to get the mass moment of inertia about this axis or about this axis. Okay, but I'm not gonna do that, but it's possible, okay? But you should know what that means. So let's say that I give you a body, and I tell you that x-axis is this way, and y-axis is this way. If I ask you to get the mass moment and the z is this way, okay? X, y, and z. If I ask you about the mass moment of inertia about z, so that means the resistance of this body to rotation about z. So I'm looking for all the masses that can rotate about z. If I'm asking about the mass moment of inertia about x, so it's all the masses that can rotate about x. So we measured them like, because r is the distance of the mass with respect to the axis that we get the moment of inertia by. So if I'm asking you the mass moment of inertia about x, so r is measured from the x to the mass that you are looking for. If I'm asking to the mass moment of inertia about y, so the mass measured from y. If I'm asking about the mass moment of inertia about z, so all the masses here measured to the axis that I'm looking at. If it's xy, so all the mass is measured about xy. Here, you will find a sphere that has, it tells you, for the sphere, like if you have a soccer ball or tennis ball, okay? Is it gonna be different, the mass moment of inertia about x, y, and z? It's symmetric about all axes. So ix equal to iy equal to iz, it is the same thing. How about rectangles? Rectangles, I about x is the same about I about y because it's the same dimension in x and y, okay? But z is gonna be different, okay? How about, sorry, I was meaning square.
Yeah.
Okay, not rectangle. Rectangle, you are gonna have x and y is different, so it's gonna be different. So here I'm giving you everything. ixx, iyy, izz, and here I have, like for the cylinder, I have the final answer, but let's prove the cylinder and look at the sheets and see if we're gonna get it right or not. I'm gonna, like, I have a cylinder like this, right? And let's say that this is the y axis, this is the z, and this is the x axis of the cylinder, and it has a height of h, so measuring from here to here, you're gonna have h over 2 and h over 2 because there's positive side and negative side. Oh, we talked about the mass moment of inertia, and the mass moment of inertia, it's r squared multiplied by dm. Do you guys remember the first moment of area and the second moment of area? There's the first moment of mass and the second moment of mass. Okay, so let's assume that we have, I just want to make sure that we have this basics before we start. If we have this mass, and this is centroid here, and we are getting the mass moment of inertia of each one of these about x-axis. This distance is positive, right? If we are getting all the masses in this block, it's going to be positive, right? But all the masses here are negative. So this r is positive, this r is negative. Same thing here. This is positive, but this is negative. If we are getting second moment of mass, which is the mass moment of inertia, r squared multiplied, it doesn't matter if it's positive or negative because r is going to be squared. So if it's a negative, it's going to be squared and it's going to be positive. So you are going to have all these four blocks as a positive thing. But if we are getting the first moment of a mass, so the first moment of a mass about the CG is always 0. Why? Because you will have this mass crossing this mass and this mass crossing this mass. So it's called RDM. About the CG is always equal to 0. Okay? But you can get RDM about another axis. Right? That's what I want to say. Same thing with this, the first moment of area is always 0 about the CG. Anyway, let's get back here. For this example, I'm asking you to find number 1, I, Z. How can we get I about Z? Okay? So we have the general rule of I, IZ is equal to the integration of R squared dm over the entire mass. But the thing is, I don't want to deal with mass, I want to deal with volumes because I know the volume of this cylinder, so I need to convert the mass to volumes. So this is going to be equal to the integration over the volume. I have to throw outside R squared dV. Okay? So this is the same like this. Alright, what I want to find out, how can I get a dV as a function of R? The thing is, what we were talking about here, we are taking a single element of the mass like this, and I take it like this. It has dx and dy because this shape is not regular in x and y. It has different shape in x and y, but the cylinder is regular. We can find a d volume that has the same r like this. Like let's say that we cut at this cylinder and we take a strip. Something like this. strip like this. Okay? So all the masses on this cylinder are at the same R. All of them have the same R. Okay? So all this mass, all these pieces have the same R. So I can take a strip, or I can take a dV that are at the same R from this cylinder like this. Okay? If I look at the cylinder from the top, it's gonna be something like this, and my strip is gonna be something like this. Right? So this is X. This is Y. And for example, let's say this is X. Right? So let's find the D volume of this small cylinder inside the big cylinder. How can I get the volume of this cylinder? You guys know? I can get the area of this small piece. Let's call the thickness is dr. Because this is r, so if you take a small piece on the dimension of r, so it's gonna be dr. This is the thickness. And if I take this thickness or this small strip and I fold it down and I make it like something like this. Looking at the top of this, it's gonna make like this. What is the length of this if I cut it like, it was like this, 2 pi r, and what I did, I made it like this, okay? So the area of the top is gonna be 2 pi r multiplied by the thickness, because the length is 2 pi r, so this I know it's 2 pi r, all this, and r is the distance from here to here at the general distance r, okay? And this thickness is it's r, dr. This thickness is dr. Like I take this and I cut it here, and I unfold it, there's gonna be something like this. So I got the area of the top, but it has a height edge, right? So if you wanna get the height thing, so it's gonna be something, if you looked at it, it's gonna be something like this. Something like this. This is 2 pi r, and this is dr, and the height is h. So if you want to get the d volume, this piece is the d volume out of the big volume. Is going to be the volume of this this part. So it's going to be, this is the area, is going to be 2 pi r dr multiplied by h. So this is dv. So I got dv, so I can plug this in here. So here I can write that iz is equal to the integration. I have the rho outside. You have rho squared multiplied by dv, which is 2 pi r, and this is dr multiplied by h. But you know what? There's lots of variables here, but I can decrease these variables knowing that the volume. Can you guys tell me what is the total volume of this cylinder? The volume of the cylinder. No. The volume of the cylinder, like if you want to find the volume of a cube, the area of a rectangle, the area is area base height, right? How about a circle? 2 pi r squared. This is the area, and the height is h. So it's pi r squared multiplied by h, right? So the volume is pi r squared multiplied by h. So what I can do, but I don't know, let's do it after the integration. Let's integrate this first, and then I'm gonna substitute with this. Because here I have r squared, r dr, I have 2 pi constant, I have h, so I get all the constants out, rho, and I have 2 pi. What else is constant? The height. So I will be left out with the integration of r cubed dr from 0 here. So I want to, like, assuming this cylinder, so this is the big cylinder, okay? So what I did, I take a small cylinder inside that has r0, and I integrate from r equal to 0 to r equal to the big R. So this is from 0 to r. I have my cylinder like this from the top. I wanna integrate from here until I go all the way down to the big R. So this is gonna be 2 by rho h multiplied by r to the power 4 over 4 from 0 to r. So this is gonna be rho by, this is gonna be over 2, and you will still have the r to the power 4 when I substitute with this, multiplied by h. So right now I can plug this in here, but this is r capital because I'm getting the volume of the entire cylinder, r, so it's by r squared h. So I have by r, I can take r squared from the r to the power 4, so this is gonna be equal to the volume. Okay, so rho by
R squared.
and this is gonna be r squared, and then this is gonna be h, so you'll have rho v over 2
R
multiplied by r squared, and rho v is the mass, so this is gonna be half m multiplied by r squared. So the I of the cylinder about z is equal to half the mass multiplied by r squared. Let's check. Yeah, so that's what we have here. IZZ is half m multiplied by r squared. Okay, so you might get a question like that, something like this. If I want to make this more difficult, I can make the r exchange over the height. Like not a cylinder anymore. Maybe it's something like a cone or something like this, and the cone is constant, like r is constant, so it's gonna be something, for example, like this. The r is 0 here, and it goes to a capital R here. And I tell you what is the function of this. Like this is a curve that has y equal to x squared. And I believe I put this, or y squared equal to x. Okay, so it is the same thing. Okay, but all what you have to do at some point, you have to plug something with this function, y squared equal to x. And I solve it here, there's just the 3 lines, but the concept is the same. You are gonna take like more, and then you get what is the volume of this, and then you plug the whole thing. But I was asking actually this problem not about z. I believe I was asking about, oh yeah, it's about z, but I call it y. Like I call this y, and I call this x. Okay, it is the same thing. I solve it here, just read the solution, and you will figure out how this looks like. Yes? Look. Oh, I was trying to figure out how to plug the volume, like remove the values that has the volume. So I have y and I have h. So I remove the y and I remove the h so that I don't mess any variables. And this is r to the power 4. I take r squared out, and this is giving me the volume. So rho multiplied by volume is the mass. Okay? So actually, this we can call it. Okay, I'm gonna put it down here without any crossing. So you'll have pi rho h over 2 multiplied to r to the power 4. And what I did here, I divided the r to the power 4, and I can remove the 2 and put here r squared and put here r squared over 2. This part is the mass because pi r squared multiplied by h is a volume, multiplied by rho is a mass, and this part is r squared over 2. So half m r squared. Okay, so just like separation of variables, so that I can. Yeah, actually, this problem is gonna be way more difficult if I ask you about. Okay. Like here's the cylinder. if I ask you about the IY, like this is X, let's say, okay, this is Y, and I ask you the moment of inertia of this cylinder about Y, it's going to be very, very different. Why? Because we need to find a mass that has a uniform distance from Y. So I can take actually a strip here from this cylinder. All this is strip, all this mass has the same moment of inertia. So I can say that this is my dm and it's at a distance, for example, distance d. I call it here y distance. That's okay. Right? So, but the mass, we need to get the d mass here. Okay, we need to find out what is, but the thing is, when I cut here, it is not like this way. I mean, like, the way that we did it was the cylinder. We take a strip, and this is strip at around the CG, around the axis that we are taking the moment of inertia. So, like here, this circle is about my CG here. Okay? So I'm taking still the moment of inertia about the CG, but this one, the x is down. Like the CG of this mass is here. So what I want to find out, I want to find the moment of inertia about this mass, about this axis, and then transfer this to here. So I need to do parallel axis theorem. So I need to find, let me tell you, what if I take a strip here, how this is going to look like? If you take a strip from a cylinder, it's going to look like a disc, right? Disc like this, right? Like I have my cylinder, solid cylinder, and I take a strip, and this strip, I take it out, it's going to look like a disc. You know, the CD, it's going to be something like this. So you need to find the moment of inertia of this disc about y-axis. I'm not sure if I have a circular shape here, but I don't. But it's the same thing. Like if you have a cuboid and you take a strip, it's going to be something like this. You need to find the moment of inertia about this, it's a CG verse, and then you transfer it down there. So it's going to be way more difficult. And actually to get the CG of a disc about y-axis, like, okay, this is my y-axis, so if I look at the top, my y is equal to this. You need to find the moment of inertia about y, so you need to have this verse. Let me actually explain it very quick in 2 minutes. I'm not going to ask you such a difficult question in the exam, never. But I just want you to understand if we are going to do it, how it's going to look like. Let me ask you, if you have a disc like this, and I ask you to get the moment of inertia about y-axis. This is, there's x and y. And if I want to find the moment of inertia of this body about y, we're going to do the same thing. We need to take a strip. This is strip. And you get the moment of inertia of this strip about here. And you integrate from r equal to 0 to r equal to r. But this strip is keep it changing with distance. Like the strip here has a length 0, but here has a length, let's say that this is x, and this is x, 2x. So the thing, how we do it, we do only 1/4, and once we finish the quarter, we multiply by 4. Like we do something like this. And this x keep it changing. Like when it comes here, this x has a value, and when it comes here has a value of r. So we need to find this as a function of r. This is r. So x, and this is theta, so x is equal to r cosine theta. Here. Right, this is theta, so this is r cosine theta. So we need to substitute this x, and it's a very, very long problem. And once we find the moment of inertia of this disc, we need to go back to the cylinder and then multiply by mass mv squared. So it's really, really complicated. That's why we give you the mass moment of inertias all here. I'm not going to ask you to drive mass moment of inertia in the exam. So, because this is not a class for mass moment of inertia, but you need to understand where this mass moment of inertia came from. Because that's a very, very basic. I believe maybe it's in the FE exam. There's definitely some questions about mass moment of inertia. And this is a really, really tricky question. And I believe this is the most difficult problem problem to get mass moment of inertia and understand it. Like a circle, and then you divide it into quarter, and each quarter you get it in a piece, and this piece you need to integrate it from 0 up to r and keep it changing. So you need to find how x is a function of r, and actually we'll end up with lots of sines and cosines once we finish this, and you have to use some sine rule. So it has background in math, background in physics, background in mechanics, everything in one problem. So it's really, really, I can put a YouTube video, not for me, like there's lots of YouTube videos to solve these problems, but it's good to look at it. So okay, so right now we understand some basics about mass moment of inertia. So let's solve one problem about this, and next time we are gonna use, while I'm doing this whole lecture, how we are gonna use the mass moment of inertia in this equation. That's what I'm doing. I don't care about I want just know the value of I so I can solve for the moment. But you need, as an engineer, to know where is I how can you calculate I, where it comes from. All right, so let me solve a very quick example to make sure that we have the mass moment of inertia. Maybe there will be a quiz. I'm gonna tell you in the announcements about the mass moment of inertia to get some properties, but it's gonna be simple, like not complex as these stuff. So here, I have something like this here, this hammer. Mass moment example. Mass moment of inertia. Example. Okay, so for this body, I'm asking you to find the mass moment of inertia about point O, and I'm asking you to find the radius of gyration, and also to find the center of percussion. So three things. Number one, the mass moment of inertia. Since I said IO and this is point O, I didn't say IG or I bar, so that's the moment of inertia about O. The number two, I'm asking about the radius of gyration. I'm just gonna say I or K. You can name it whatever you want. Number three, center of percussion. These are the three things that we need to find out. Okay, to find the mass moment of inertia about O, I need to find the moment of inertia at the CG verse and then transfer to O. Okay, so I have this bar has a length of 5 foot, so definitely the CG is somewhere here at 2.5 foot from here. And this is 1 foot, so definitely the CG is something like that. So we are not gonna derive the mass moment of inertia of this body. You'll have to go here, and actually didn't provide any thickness here. Since I didn't provide any thickness, we call this here as a bar. We don't care about the thickness. It's a very, very thin, so we call it bar, and it has a special moment of inertia. And it's only function in the length, it's not function in the width. But this one has a width and depths are the same, so definitely have Ix and Iy. All right, and IZZ of this bar is 0 because we neglect the mass about Z, because this is very, very tiny mass. So if the mass is very, very small, so the mass moment of inertia is going to be, because Dm is going to be 0, So I is going to be 0 because we neglect the mass around the z-axis. But right now we are not calculating about the z-axis. Let's see, because this is very important. This bar, what is the moment of inertia when we talk about the moment of inertia about O? If this bar is rotating about O this way, it's like a hammer, and this hammer is bent here, and let's say this is XX. So, I'm not sure, do you guys have the sheets? Do you guys have it right now? Look at the bars and tell me, which one should I use? IXX, IYY to represent I about O. First, I need to find the ICG, and then I transfer it to O. But you need, for sure, to know the what axis that we are looking at. So this is the bar that we have, for example, okay? And this bar we are looking at, like this is the CG, we are looking the mass moment of inertia about acts like this because it's been somewhere here. But I'm gonna look at the mass moment of inertia at the CG, how it rotates this way, and then I'm gonna look at how it rotates at a different point. So I'm looking at either this axis, right? So let's see what axis. It can be X, it can be Y. So as you see here, IX equal to IYY is equal to 1 over 12 ML squared. Okay? And also gives you, if you are looking at the moment of inertia about this point, it's also given. It tells you Ix dash and Iy dash is equal 1 over 3 ML squared. Okay? So if you are looking for a mass moment of inertia about this point, it's given. If you are looking at the center of mass, it's given here in this equation sheet. But I'm not looking about how this pin is gonna rotate about itself. Like I'm not looking at this. I'm looking how it's gonna rotate this way, not this way. Okay, do you follow me? Like it's something like this. Okay, I'm not looking how this pin is gonna rotate about Z. I'm looking how it's gonna rotate about X. Okay, like or about this way. All right. So I'm gonna use IXX or IYY, which is the same. So if we, and this is body number, let's say that this is body number 2. I name it A and B, or 1 and 2. So this is W1. I give you W1 is equal to 12 pounds, and W2 is equal to 4 pounds. So that's body number 2. So let's see body number 1. Okay. All right. For the thin plate, like a plate like this, like that has a small thickness, because I didn't give you a thickness, that means that the thickness are very small. It's not a solid thing. So the thin plate, it's a square, has 1 and 1. Okay, leave. Yeah, there's the number here, not wrong, but okay. So alright, so here if you look at this one, like let's assume that this is a plate, and we are looking at how this plate is rotating about the CG this way, so we need to find how this is going to rotate here and then transfer it to this, because we are looking at the moment of inertia about O. Same thing, we're going to look at the moment of inertia about this point and then transfer it here, and this point and then transfer it here. So we're looking at the moment of inertia, how this body is moving this way, so I need to find the axis perpendicular to this point. Not X, not Y. Not X, not how this body is going to rotate about this way, or how this body is going to rotate this way. And that's very, very important because you are given